Please help me welcome our speaker for the morning, Dr. Gregg Hallinan, Caltech Professor of Astronomy and Director of Caltech's Owens Valley Radio Observatory, is with us this morning to present his plans for the Deep Synoptic Array, the DSA-2000, that will be, in his words, the largest radio telescope ever built, with the promise of becoming a world-leading radio survey telescope and multi-messenger discovery engine. Gregg Hallinan received his PhD in astronomy from the National University of Ireland, Galway, now the University of Galway, in 2008, and joined the Caltech faculty in 2012. In addition to his work with OVRO and DSA-2000, he is involved with a series of other projects that we may get to ask him about as we go through today's presentation. Earlier this year, he and Professor Manzi Kesliwal were named recipients of a New Horizons Prize in Physics. According to the award citation, they were honored for leadership in laying foundations for electromagnetic observations of sources of gravitational waves and leadership in extracting rich information from the first observed collision of two neutron stars. Professor Gregg Hallinan, welcome to the Greenway Talks at Palomar Observatory. Thank you for taking time to speak with us today. We'll take questions at the end of the presentation, including any questions that are typed into the chat, and we're pleased to take questions from our live studio audience. You know what it is. For that reason, I'll ask everyone now to turn off their microphones. And with that, Professor Hallinan, please, the floor is yours. Have we
unmute yourself?
There we go. Try if you try it again.
All right, that's much better. Okay. I wasn't able to share. I also can't share my slides yet, Steve, until you either make me co-host or enable screen sharing.
I thought I had made you a co-host. I did not. You're right.
Okay, only you can make him a co-host.
Only
you.
Only you. There we go.
Got him.
All right, here we go. All right, thank you very much for the generous introduction, Steve, and it's super nice to be here with you all this morning. I'm going to talk about the DSA-2000, but I'm going to take a meandering journey through history and projects to get there, to outline the motivation for why we're building the most data-intensive science experiment ever built and what will be the most powerful survey radio telescope ever built. First off, a confession. Despite being a radio astronomer, I probably share something with you all in that this is my favorite telescope on the planet. I have spent a lot of time at Palomar, and here's a photograph I took many years ago while building an instrument for Palomar. It's a very special place. And despite being a radio astronomer, it remains my favorite telescope, and has been since my childhood when I read about the mighty 200-inch in books and so on. And I had the great pleasure of being able to build one of the instruments for the mighty 200-inch. This is Chimera, the Caltech high-speed multicolor camera. This is it. This is a picture. Here's the instrument with my former postdoc and the instrument scientist, Leon Harding. Here it's being winched up into the prime focus of the 200-inch. And here's a photograph of myself and Leon in the prime focus all those years ago. And I want to just mention it because, like I said, I spent a lot of time at Palomar. And here's an example of what this instrument can do. It can go really, really fast. So here's a movie of the Crab pulsar, which spins at 30 times per second. And here's the Crab Nebula, and here you can see the pulsar pulsing right here at a speed of 3 times per second. That is an object that's only 20 kilometers across. So very fond of Palomar, and this instrument is operational and used by many faculty for a lot of science. Okay, I want to also just point out in the, along the lines of the talk I'm about to give, sensitivity is one very important metric for a telescope. How big is your bucket? And of course, for most of the last century, the biggest bucket on the planet was at Palomar. It was the Big Eye. Well, another very venerable telescope, of course, is this one, and this is the Samuel Oschin telescope, which has a combination of sensitivity, much less sensitive than the 200-inch, but it has a huge field of view, which means it has a different metric where it excels. Survey speed, how fast it can survey the sky to a given depth. It can survey the skies much faster than the 200-inch, for example, despite being a much smaller aperture. It relies on this Schmidt camera technology built by Bernard Schmidt in the 1930s and first demonstrated on the telescope that Steve mentioned a few minutes ago, the 16-inch Schmidt camera. So this is an example of a survey telescope, and this telescope has had a tremendous impact on astronomy despite its small aperture, and still does to this day. It is used for the Zwicky transient facility, and I'm sure you have already heard about this before. I'm just going to show you the field of view of the Oschin telescope using the camera of ZTF, and it now surveys the skies looking for transients, new sources of optical light in the sky, and it's quite a huge field of view. Here it is shown with respect to Andromeda, but also on the right you can see the Belt of Orion and Horsehead Nebula, etc., captured by this enormous field of view, 47 square degrees. Another thing about myself is that I'm, maybe like many of you, I have been since childhood obsessed with astronomy, and long before I was a professional astronomer, I was an obsessive amateur astronomer, and I still do that to this day. How I do it nowadays is I use big telescopes for my day job, and at nighttime in my backyard, I image the planets. So here are a couple of images from my backyard of Jupiter and Mars. This is Mars from last week, actually, and I was out there last night, and I'll be out there again tonight. And in the best case scenario, I'll be on Mount Wilson, because of course Mount Wilson has much better seeing than down on the ground in Pasadena. But yeah, so like I said, like you all, I have the same passions. But this is a lecture about radio astronomy, which is definitely my day job. And to get us on track with that lecture, I'm going to start off with some history. Radio astronomy is a much younger science than optical astronomy, which goes back centuries, a millennia in some senses. It uses radio waves. So like optical telescopes, radio telescopes measure light, but it measures light at a much longer wavelength, at radio wavelengths. And when the field of radio astronomy began in the 1930s. This is Karl Jansky, an engineer working at Bell Labs, who built this rather ridiculous-looking device to measure sources of interference that were being seen by the Bell Lab communication antennas. And what he found was a source of noise in the sky that was unexpected. And through some careful deliberation, he realized that source of noise was not moving with the Earth, but moving sidereally with the sky. It must be outside of our terrestrial sphere. And in fact, he eventually realized it was coming from the center of our galaxy. And that was the cause of that radio emission wasn't explained for decades, but that was a huge discovery. Here's the New York Times front page mentioning of this discovery, and indeed Jansky would have won the Nobel Prize if he hadn't died at a very young age, unfortunately. But in radio astronomy, a lot of things are named Jansky, and in fact, I was a Jansky fellow, for example, many years ago. So he is well remembered. So Caltech, being Caltech, was very quick to think about, well, what does this mean? And actually, a professor of physics and a student actually went out into the Mojave Desert and replicated the result, not using this antenna here, but with a small antenna, and proposed, why don't we get into this new emerging field of radio astronomy? And they proposed to build this very large antenna. And they asked someone to draw it, and the person they asked to draw it is, of course, Russell Porter. You might recognize the style of drawing. So as well as doing many drawings and designs for the 200-inch, Russell Porter did this drawing for this physics professor to propose this radio telescope. They asked for $1,000, and at the time, Millikan decided not to fund it, and that was the end of that early attempt to do radio astronomy at Caltech. It was another decade or so before the field took off, and it took off in Australia, and it took off in the Netherlands, and took off in the UK, and it was actually mostly radar engineers coming back from World War II that kind of took up the field. Caltech did not get involved until about 20 years later, when a very famous astronomer, who really was the person who started the astronomy department at Caltech, Jesse Greenstein, realized this was a very important new field to explore. And here he is shown by a more famous Russell Porter drawing. So at the time, there was not really an established presence for radio astronomy in the US. Like I mentioned, it was happening in Australia and in the UK. So Jesse decided to try to convince two radio astronomers from Australia to come to Caltech to begin Caltech's radio astronomy program. John Bolton and Gordon Stanley. And in particular, John Bolton would be the first director of this new observatory. Here he is as a young man, and he was a young man while at Caltech. He went back to Australia and actually became the person who built the Parkes dish. If you ever saw the movie The Dish, he is played by Sam Neill in that movie. That's the same person. But he was the very first Obro director, which is the role I hold today. And before they actually found a site for Obro, they wanted to build a first dish, and the obvious place to build it ended up being Palomar. So the first Caltech radio telescope, in fact, was not at Obro, but was at Palomar. Here's a photograph of that first telescope with John Bolton hanging off it, and you can see the mighty 200-inch in the backdrop. But eventually they went ahead and found a good site. Palomar did not have enough available area and was actually pretty, for optical astronomy, being on a mountain is good. For radio astronomy, it's bad. You want to have isolation from everyone's, terrestrial signals. And being in a valley is much better than being in a mountain, actually. And they ended up finding a quiet valley, the Owens Valley, nestled between the Sierras and the Inuit Mountains, where you get that shielding of all the interference from Los Angeles and San Francisco and Las Vegas. And here's the footprint of the observatory. It's quite close to the small town of Big Pine and Bishop. It's about a couple of square kilometers in area. And the very first telescope they built was two 90-foot antennas in 1958. And these were the signals from these antennas were combined via a technique called interferometry, which I'll explain in a little while. At the time these were built, this was the biggest interferometer on the planet, and it made huge groundbreaking discoveries. Not unlike Palomar, it had quite a public, an impact on the local population, and they gave it a nickname. And I wonder, can anyone on this call guess the nickname they would have given these telescopes? Well, they are called the Big Ears. And of course, the parallel is the big eye at Palomar, and that's not a coincidence. So this was the very first two telescopes that were built in 1958. In the next 10 years, they began great plans to build a bigger antenna, but not just one. They were going to build 8 40-meter antennas, which was absolutely transformative. This was actually going to be the radio equivalent of the Palomar telescope, this huge leap in sensitivity. It was going to be called the Owens Valley Array. The project got approved by the National Science Foundation, and they were given money to build the first antenna. This antenna actually is, a lot of the construction was done by Westinghouse, not unlike, of course, the 200-inch. So it has the same sort of Westinghouse battleship feel to the telescope. It is quite a huge structure. And this structure came online in 1968, and of course they met their requirements and came back to NSF for more funding. Meanwhile, a new fledgling national organization called the National Radio Astronomy Observatory brought forward an alternative design. Instead of building 8 40 meters, they proposed to build 27 by 25 meter telescopes, and they wanted to call this the Very Large Array. So even though this had been already approved, a panel was chaired to review whether or not which design should be built, And the person who was appointed to be chair of that panel was none other than Jesse Greenstein, the same Caltech professor that had started the observatory. And in the end, they decided to go ahead with the alternate design, the Very Large Array. And that meant that Caltech was not building that huge, world-leading radio telescope, but it was actually the National Radio Astronomy Observatory. And this, of course, is probably the most iconic radio telescope of all time, and my second favorite radio telescope after Palomar. Caltech radio astronomers were not very happy with our Jesse when this happened, and they accused him of stabbing him in the back at the time, but actually it was the right choice. It was a more modern design. The negative impact was it came online about 10 years later than the original plans for the Owens Valley Array. So the Owens Valley Array never happened, but I will point out that in the 2013 movie, Man of Steel, Superman movie, which was partially shot at the Owens Valley Radio Observatory, they actually, via CGI, duplicated the 40-meter antenna. So we finally got to see what the Owens Valley Array would have looked like. All right, fast forward to today. There's been a lot of amazing history that's happened in the interim at the observatory. There have been multiple generations of new telescopes led by many professors and successive directors. There have been hundreds of graduate student theses across the US and even worldwide using science at this observatory. And every time a new direction that was started at the observatory seeded essentially what was going to be the next national facility. So I mentioned the Very Large Array having its history at Avro. Very long baseline interferometry, the technique of combining telescopes all around the world, was also pioneered here and became another focus. And then finally, observing at very high radio frequencies was also pioneered here and led to the array ALMA, which is the most expensive ground-based telescope in the world. So it really has seeded generation after generation of new telescope. You can learn all about Avro. It's in this picture behind me, preventing you from seeing my son's bedroom. And you can learn all about our projects. We have an array of cutting-edge modern projects that are ongoing at the observatory. We operate from the lowest radio frequency operational from the ground, about 10 megahertz, all the way up to a few hundred gigahertz. So spanning a range of wavelength / frequency of about 10 to the 4. So it's like operating from, optical almost, or from the far infrared all the way through to ultraviolet all at once. It's a pretty spectacular range of wavelengths. And I'm going to come back and talk about our most modern projects in a little while. First, I want to introduce a concept that may not be obvious, which is what is an interferometer? Why do you see arrays of antennas in radio astronomy? You don't see typically arrays of optical telescopes where their signals are combined. Why do we do that in radio astronomy? Well, there's a fundamental problem we have with radio telescopes. This is the largest single steerable radio dish in the world. There are bigger dishes, but they're not really steerable. This one is fully steerable to anywhere on the sky. It is not located in either Washington or New York. This is to give you a sense of the scale. This is a huge, huge mechanical structure. It is about 100 meters across in diameter. So this is an enormous structure, and this is for scale. But despite this enormous scale, it actually has very poor spatial resolution on the sky. Your eye actually has better resolving power than this telescope. And that's because the resolution of a telescope depends on how many wavelengths fit across that aperture. Now, your eye observes visible light with a wavelength of 500 nanometers, right? So that's a very, very small wavelength. And you can fit actually quite a large number of those across your pupil. This operates at centimeter wavelength, and the ratio of that aperture to that wavelength is actually smaller. So your eye has better resolution. And the problem we have is building a larger durable structure is basically impossible. Mechanical engineering limits us. This costs hundreds of millions of dollars to build. So what we do is we synthesize an aperture. We actually connect together the signals of lots of smaller antennas to create a synthetic aperture. And we connect their signals via a technique called interferometry, okay? So, this telescope on the left, like an optical telescope, the light from the sky bounces off the mirror and comes to a focus up here on the at the focal plane. Here, what we do is we actually measure the signals from every antenna, and we make the image in the computer. And that's how we create an image with an interferometer. So it's very different. Now, a very important part of this, in order to do this, we have to interfere the signals of every antenna with every other antenna. And we don't make images immediately. We have to take that data output, the combinations of the signals from every antenna, which we call visibilities, and then we make that image offline. And it turns out that the computational cost of combining those signals is proportional to the square of the number of antennas. So if because you're combining every antenna with every other antenna, you end up, if you double the number of antennas, you get 4 times the data. And back when the VLA was being built in the 1970s, computers were much less sophisticated than they are now. So it made sense to try and build a small number of big dishes and try to minimize the cost of the computer in making that image. And that's why we have very, very big radio telescopes historically. Either a single dish. This is the glorious, unfortunately now no longer operational Arecibo dish on the left, and on the right we have the very large array that I just described. And because these antennas, because the cost of the signal processing was so large, they're huge. Rather than building lots of small ones, you build these small number of big ones. And that's why they're so iconic, right? This is the VLA getting blown up in Terminator 4, and here it is, Jodie Foster listening for aliens in the movie Contact. P.S. You can't plug your headphones into a radio telescope, I'm sorry to say. And of course, here is James Bond dangling over Arecibo. These are iconically large structures. But that focus on very big antennas is because these were built many decades ago. Arecibo was first built in 1963. It was upgraded after that, but that was when it was first built. The Very Large Array is older than me, and that's saying a lot. I'm feeling it now. It's built in 1980. And of course, we lost Arecibo recently. Nonetheless, by combining those signals together, you can make images with spatial resolution comparable to optical telescopes. Here is an image of the Crab Nebula made with the Very Large Array at a frequency of 5 gigahertz. And the field of view is a few arc minutes, and the resolution is about an arc second. And that maps very well to optical. Here's that same image I showed you earlier on. It was a movie earlier on. Now it's an image of the Crab Nebula and the optical chimera. So you can see it's kind of really useful to use an interferometer to be able to make images that map well to the resolution we have in optical telescopes. And actually, using this technique of interferometry, we can build telescopes that are far better resolution than any optical telescope, including the Hubble Space Telescope and JWST. Radio telescopes hold the record for the most precise or highest spatial resolution images ever created. Here's the record holder, actually, and you've probably seen this before. I think Katie Bauman gave a talk at one point. By building radio telescopes across the entire planet and bringing them together, you can make images that have resolution that's maybe 1,000 times better than the Hubble Space Telescope or JWST. And this is how we were able to resolve the photon ring and shadow of a black hole in a nearby galaxy. This telescope has a resolution of 50 microarc seconds. That's enough to resolve an orange on the moon as a kind of point of reference. A random one, but it's a relevant one. But we are not working with the same kind of mirror you have in an optical telescope. In this telescope, there are a few locations across the planet where the telescopes are located, but you're only sampling a small fraction of your synthetic telescope. Most of your mirror is empty, if that makes sense. And working with a shattered mirror gives us a lot of problems. So let me kind of go back to optical to give you a point of reference. This is a wonderful Hubble Space Telescope, another very venerable telescope. It's the Palomar 200-inch of its time. And on the right is an image of a star field with the HST. And as you can see, you have this quite aesthetically pleasing effect of what we call diffraction spikes on every star. But why does that happen? It happens because the Hubble Space Telescope is not a single solid mirror. There is a hole in the center to allow light bounce through the instruments. There are some struts to support the mirror. And that missing space leads to artifacts like the ones you see in the image over here. And really what happens, what matters is this aperture defines the response of the telescope to a point source. It's what we call the PSF. And the PSF of Hubble has this shape because of those struts you see that support the mirror. So every point source that it sees, like a star, has that exact response where you see those diffraction patterns, right? Now, we're only missing a small part of the Hubble Space Telescope. With the VLA, we're missing most of the information that's meant to be hitting. We're trying to synthesize an aperture a kilometer across here, but most of the information is not actually, hitting a telescope. And that gives us a point spread function that's pretty horrible compared to what you see for an optical telescope like Hubble. And what does that mean? It means you can't just make an image in a deterministic, easy way. We have to take the data from those pairs of telescopes, and poor students have to spend weeks and weeks of blood, sweat, and tears just to make one nice image. It's very expensive computationally, and it's very intensive for your poor students and postdocs to do. And this is a typical picture of a radio astronomer because the data volumes are very large, the process is very slow, the software is very buggy and not very well optimized. And we have a problem where the amount of data from radio telescopes is actually stifling the science. And the VLA, this is even with the Very Large Array, which is a 40-year-old telescope. There are new telescopes coming online across the planet. These ones are the ones that already come online, and there are ones coming online over the next 15 years, including the Square Kilometer Array, a much bigger array in South Africa and Australia. And then there's a next generation Very Large Array coming online, where they have way more telescopes. And remember I said the amount of data goes as the square of the number of antennas. So we're actually on this curve of creating so much data that astronomers are going to have major problems. Now, I have a plot that shows this. It's my only sort of like data plot that shows how the data rate is changing with time based on how many antennas we are building for these new telescopes. The Very Large Array about 13 years ago, produced about 0.1 terabytes per year of data. It went through a major upgrade, and that increased by a huge amount to about a petabyte a year. And we, as an astronomy community, are struggling with all that data. That data goes on an archive, you download the data, you make your images. These next generation telescopes are going to produce more like an exabyte per year of data. So it's increasing at a rate that's much faster than we can handle with computers. To put it in context, this is the worldwide internet traffic this year, which is almost 5 zettabytes per year. That's 1 million petabytes a year. We are rapidly approaching this line. So how do you deal with the world's internet traffic of data if you're trying to make your radio telescope images? Well, at Caltech and at Observatory specifically, we are building new generations of arrays where we're actually embracing this problem, where we're saying, let's not build 100, let's build thousands. And it turns out by building very large numbers of arrays, here are 2 arrays we've already built, and the future we're going to build is called the DSA-2000, where if you build enough antennas by some magic, you get a new type of capability called a radio camera, and you can make images in real time for the first time, and the problem goes away. And we are on this path to this incredible instrument called the DSA-2000. These first 2 arrays that are already built are funded by the National Science Foundation, and the DSA-2000 design is well underway, and it's funded by Schmidt Futures, which essentially is Eric and Wendy Schmidt's philanthropic efforts to stimulate new science projects and solve big data problems. Okay, I'm going to talk quickly about these 2 arrays as examples, and then really get on to this, world-changing telescope. This is the LWA. This picture is quite beautiful. It's not usually this green in the Owens Valley. This array images the entire sky every 10 seconds. So this is the radio sky rotating above the Owens Valley as imaged by this array. It operates at very low radio frequencies, sort of down below the FM band. And I talked about the Crab Nebula and Crab Pulsar. This is the Crab Pulsar pulsing in this movie. You can see, it'll show up here in a second again. We can actually watch the Crab Pulsar rotating overhead. Every source you see here is a supermassive black hole halfway across the universe. It's very different to what we see with our optical eyes. And you can see airplanes passing overhead. That's an airplane. You'll see one here going across the array in a second. There's one, that's an aircraft. And what we're seeing there are like microwaves, someone's microwave in Las Vegas bouncing off an airplane passing overhead and landing on the array. So we see the entire sky. And to do that, we actually combine the signals from every antenna, and we have a huge data rate, a terabit a second. But it gives us this amazing capability to see the entire sky at once. Why do you want to see the entire sky at once? Because it helps you with a very key science case related to exoplanets. As you may be aware, we now know of more than 5,000 planets orbiting of the stars. When I was a kid, we knew of 9, that became 8, and now we're up to more than 5,000. This dipole array of 352 antennas searches for radio waves from those planets. Now, we're not looking for alien life. What we're looking for is actually radio emission from the magnetospheres of those planets. So the Earth has a magnetic field that shields us from the sun's activity. Mars does not, and it lost its atmosphere when it was a young planet. So it may be a very important ingredient for life. And we want to detect whether other planets also have those magnetic fields. And it turns out how we can do that is to look for radio emission from those planets, and you can measure how strong that magnetic field is for those planets. The problem is it only really gets bright when the Earth, for example, has an aurora. That only happens very rarely. And what we do with the LWA is we actually image the entire sky, and we monitor every single star and planet system out to about 80 light years, looking for the radio emission produced by those magnetic fields. This is the location of all of the small stars, what we call M dwarfs, and the yellow objects are all of the sun-like stars. And we monitor them continuously to look for evidence of exoplanet magnetic fields. And we actually also have a small optical telescope under construction at Palomar that will look for the optical emission from their parent stars when they produce a flare, because that's when we expect to see the aurora, when you have a big solar flare, and that hits and the material thrown out from the star hits the planet. So that's an example of what you can do when you build small antennas that can see a lot of the sky rather than big ones that see a small part of the sky. I'll give you one more example. This array can also detect cosmic rays that hit the Earth's atmosphere. These are the highest energy particles we know in the universe. We do not know where they come from. We can figure that out by detecting the air showers they produce. And this dipole array, we can see that radio emission. Now, to do this, we have to look at the signal from every single antenna at a time resolution of 5 nanoseconds. And that requires us to look at a terabit per second of data. So 140 gigabytes every second. So basically, it's almost like fitting your hard drive every second and trying to analyze it. It's very data intensive. But when you do that, you can actually see these cosmic rays. So here's an example of the footprint of that array. And I'm going to play a movie where we look at the radio power at a time resolution of 5 nanoseconds. So slowing it down by a factor of 100,000, you can see an air shower cross over the array at the speed of light. So we can easily resolve the speed of light across the array. That's how fast we're sampling. So here's an example of this movie. And that is the air shower from a cosmic ray traveling across the array at the speed of light. My graduate student who developed this technology actually won the Clauser Prize at Caltech, which is for the best graduate thesis across all of Caltech. Now I want to talk about the other array we have, which is the DSA. And the DSA is an array of 110 dishes. And it also has a big field of view, and it operates at a higher frequency so instead of being a dipole, we have a dish, but it's a very small dish. And what it does, it actually scours the sky looking for fast radio bursts. Every day, there are 1,000 bursts of radio waves coming from deep space. They last 1 millisecond. They come from outside our galaxy, and we do not know what causes them. We've got some ideas, but we don't know firmly yet. And they're called fast radio bursts. We're not very imaginative with our names. It's fast, and it's a burst of radio emission. The DSA-110 can actually figure out where they come from by using interferometry to get good resolution. But you have to do that really fast because you have to detect them with 1 millisecond time resolution. So we've built this array of small dishes called the DSA. It is the precursor to the array I'm going to talk about in a minute, which is the DSA-2000. And here it is now slewing across the sky, looking for those fast radio bursts. We build these antennas at very low cost. So each of the antennas in the very large array would cost a few million. We built these antennas for about $10,000 each. But per unit collecting area, they have the same sensitivity as the VLA antennas. And we have pretty spectacular technology to do that. I'll describe it in a moment. We have already, this array has been operational, came online this year. This is our assistant professor of radio astronomy, Vikram Ravi, who is leading the science with the array. And we have localized 30 of these bursts to their host galaxies. That is more than every other telescope in the world combined. So you're going to be hearing a lot about this science very shortly. So here's an example of 3 of these FRBs, and here are the host galaxies they sit on, and we are pinpointing where they're coming from, and this will really be a transformative science, a transformative impact for this field. Okay, moving on to the DSA-2000. So this is a successor to those previous arrays, and this will be the very first radio camera, and I'll explain what that is. It's going to have 2,000 dishes, which is just a huge number. And it's operating in the gigahertz radio band, the same band your cell phone operates and your wireless operates. And because it's spread across a big valley in Nevada, it will have a resolution of about 3.3 arc seconds. And this is highly optimized to survey the sky. This is kind of like the Schmidt camera in the optical. In fact, it's funded by Eric Schmidt, so maybe it's the Schmidt radio camera. And just to put this in context, this is going to change the game. These telescopes that are the venerable ones of the last few decades, the DSA-2000 can map the sky 2,000 times faster than Arecibo and 1,000 times faster than the Very Large Array. Right now, we know of every radio telescope ever built has detected about 10 million sources combined. The DSA-2000 will do that in the first 24 hours and will increase the total number to 1 billion. By a factor of 100, it will increase the number of radio sources we know. And really, it is, the next decade is the decade of big surveys. The Rubin Observatory is coming online, and their space telescope is doing surveys. This is the radio survey telescope that will basically transform radio astronomy. I showed this plot before where I said, here's how much data you produce from the VLA and from these other telescopes that are coming online in the next decade. These are billion-dollar telescopes. Excuse me. The DSA-2000 will come online in 2026. In its raw data form, it produces 0.7 zettabytes per year. That is by far the most data-intensive science experiment on the planet. In the data type you normally produce from a radio telescope, which we call visibilities, it will produce 20 exabytes per year. Just to store that data will cost 100 million per year, except we're not going to store that data. For the first time, we are going to make images, not visibilities. We are going to build the first radio camera. So we really are getting up to this, this will have, about, not far off 20% of the world's internet traffic passing through the system. But the key thing is, we're going to build a radio camera that makes images that are really small for the first time. So yeah, we have 2 technologies that make this array possible. It will cost about 140 million to build the telescope. We have the world's, best performing, low cost, uncooled antenna. So the Very Large Array and all those big telescopes have receivers that they have to be cryogenically cooled to a few Kelvin above absolute zero. We have built the world's first uncooled receiver that has performance as good as those telescopes. And the other technology is we're building the first radio camera. We're putting a digital back end on the telescope that makes images in real time. How can we do that? Well, this is why. I showed you before the Very Large Array, and it has this pretty nasty point spread function. This is an example of what an image looks like with a Very Large Array if you don't do all that processing offline. With the DSA-2000 with thousands of antennas, you have this beautiful point spread function, and you can make an image in real time that looks like this. So, and this is the same exact field. Now, the Very Large Array with lots of processing offline can get something like this, but this telescope can do it in real time. We will have 5,000 graphics processing units strapped together to make this possible, to handle all that data and make those images in real time. The other amazing technology we have is that we don't need to have any cryogenic cooling. And the reason we can do that is thanks to this gentleman right here, whose name is Sandy Weinreb. Sandy, in my opinion, is the greatest builder of instrumentation a radio instrumentation the world's ever seen. For example, he was the chief engineer that built the Very Large Array in the 1970s. And he's 85 and he's still going strong. And he invented technology that allows us to build a receiver that does not require any cooling. Normally, to just build a cryogenic cooling system would cost you $100,000. Now we can build these receivers for about $1,000 each, thanks to Sandy's invention. And it allows us to go really low cost. We've been building this over many different generations over the years, and DSA-2000 will be the ultimate final example. And what's really cool is that once you take away that cryogenic cooling, you can really push the cost down of everything else. For example, this receiver, which includes this revolutionary low noise amplifier with no cooling, we build that out of cake pans from a company called Fat Daddy-O. And we can buy these cake pans for about $70, and we strap them together. And here's actually a movie of my postdoc using those cake pans to assemble the feed that we build at very, very low cost. But the performance is just as good as those cryogenically cooled receivers that were built for the Very Large Array. Now, here's a picture of our design for the antenna. And this would be a fully steerable antenna that we build. This would cost $25,000 per antenna for this fully steerable design. We're actually building the reflector, this kind of parabolic surface, at the Owens Valley Radio Observatory using a technique called hydroforming. And this machine is currently under construction, and we'll have our first scaled prototypes by the end of this year, and we will have full-size DSA-2000 dishes by August of next year. We will have 5 of them. Now, the next thing to ask is, where can you build this telescope? Turns out we can't fit it at Ovro. We need to find somewhere new to build this telescope. It needs to have this huge area, 19 by 15 kilometers, or about 9.3 by 11.8 miles. Ovro is too small. It needs to be somewhere where there are no people, because your cell phones and your microwaves are going to completely prevent us from observing. In the same way that Palomar worries about light pollution, we worry about light pollution in radio wavelengths. This telescope could detect your cell phone on Pluto. So if you have your cell phone in the same valley, it's going to saturate everything and we can't detect anything at all. So we need to get away from your cell phones and away from cell towers. Mountains are great because mountains provide shielding from big cities. And we want to go somewhere where we can actually install a network of about 1,000 kilometers of optical fiber between all the antennas to actually to combine the signals. So here is a map of the cell tower density across the United States. And obviously the East Coast is a bad location to build this telescope. On the west side of the United States, there are a few locations where there are a few cell towers. And in particular, in the Great Basin of Nevada, there's a low density of cell towers, and there are mountains. There are ranges of mountains where you can actually try to build a telescope. So for the last couple of years, we have been scouring this location. So here's a kind of an idea of California, Nevada, and the Owens Valley Radio Observatory is in here. We have been scouring 50,000 square miles in Nevada, looking for the perfect site to build this telescope. Here is some of the team that have been driving around in these valleys with this equipment, trying to find the locations with the lowest levels of radio frequency interference. This postdoc here spent about a month by himself in these quiet valleys trying to find the ideal location, to the point where we're going to actually get him you've seen the movie Castaway, where Tom Hanks is by himself for so long, and he has Wilson, his companion ball. We were going to give him a similar ball as a present with a handprint and Wilson written on it, because he was by himself for so long. In the end, we found the perfect location. It's on this map. If you can see my mouse, it's right in here. It's a valley called Hot Creek Valley. This is a spectacularly quiet location. This just shows you interference levels. The interference levels are 1,000 times lower than the Owens Valley Radio Observatory. Here's a picture of the equipment in the valley. we measured the soil conditions. We can deploy our optical fiber network very easily. This place is incredible. Just to show you how quiet it is, there was a 1 megaton nuclear bomb detonated in the valley in 1968, about 5 miles away from the edge of the array. It was detonated underground, and it was called Project Faultless. It was called Project Faultless because the hope was it would not actually impact the local geology of the valley. It was very badly named because it actually triggered 2 geological faults to reactivate, and the whole location dropped down by about 20 feet. So gives you an indication how quiet the valley is. The only other facility in the entire valley is down here. There's an Air Force base, and it is the base camp for Area 51. So once again, just to show you how remote this location is. And we will hopefully, right now we're working with the Bureau of Land Management, and we're trying to meet with local tribes to figure out how to best be able to build in the valley. To wrap up, I want to very quickly mention some of the science the array can do. This will transform radio astronomy. There's so much science I cannot even begin to capture what it can do. Like I mentioned, it will discover 1 billion radio sources, which is a factor of 100 more than every other radio telescope combined to date. During a recent review of the project, Matthew Bales, a very eminent radio astronomer, said this one project could keep every radio astronomer worldwide busy for a decade. We have three key science themes: multi-messenger astronomy, which is one of my own focuses, tracing the evolution of the universe through cosmic time, and looking for new radio sources, the dynamic radio sky. I will mention one example, which is gravitational waves. This array won't just detect electromagnetic radiation or light, it will be able to measure gravitational waves. How does it do that? Well, it turns out a certain type of object called a pulsar, which is a spinning neutron star, we can use those pulsars to measure the distortion of space-time, because those pulsars are very precise clocks, more precise than any clock we have on the ground. By measuring the timing of those pulsars very, very precisely, we can detect the distortion of space-time by binary supermassive black holes. So it's kind of like the LIGO project, but much, much longer wavelengths of gravitational waves. And we will be the main experiment that will be used for pulsar timing. It used to be Arecibo. It will now be DSA-2000 for the US community. It will be used to detect the radio afterglows of the mergers of neutron stars. And those mergers also produce gravitational waves. And they are detected by LIGO. But to find out where the merger happens, we have to use telescopes that can detect light. And the DSA-2000 will be able to detect all or most of the radio afterglows of those mergers, which is extremely powerful. My own group detected the first afterglow for the only event we found to date. Going forward, DSA-2000 will find them at a rate of many times per year. And finally, I'll mention fast radio bursts. The DSA-110 will detect 100 per year. The DSA-2000 will detect 10,000 per year. And that will absolutely transform what we can do with those FRBs. We can actually probe the unseen matter throughout the universe with that sample of objects. Okay, my very last slide is just kind of showing our timeline. Ignore most of the material on this. I wanted to say that we actually put the project in to the decadal survey. Every decade, the US community tries to assess and rank what are the things that need to be built for the following decade. And the DSA-2000 was one of the ones that was selected and ranked as a very important project. We are now deep in the design phase. We are actually in the process of building 5 prototypes. And next year, we're going to ask for all of the money to build the project. We want to start construction in 2024. And the goal is to turn the telescope on in 4 years in 2026. So we really are moving aggressively. Okay, I'm going to stop there, and I'm going to just pop up a summary and take any questions.
Greg Hallinan, thank you very much. That was, well, I'm still working to get my head around the idea of a radio camera. Big data. It's incredibly impressive. Thank you for the presentation, and let me ask people to unmute themselves, and it's time for questions. Anybody?
I have one. Greg, I did a little computing, and it's something you didn't mention was the nanohertz experiment or array. And it means that they want to observe at nanohertz frequencies. And if you turn the equation around, the wavelength of 1 nanohertz is 31 light years. The pulsars are about 1,000 light years away. So you have probably the largest observatory ever made, because the diameter of the from one pulsar on one side to the other side is 2,000 light years. At that kind of sensitivity of 1,000 light years on either side, you ought to be able to receive things in real time that nobody's ever thought of. And I think that's one of the most exciting parts of the DSA experiment. You want to say anything more about that?
Absolutely. So this experiment of using pulsars to basically measure the distortion of space-time has been ongoing for a couple of decades. And actually, there already has been some tentative detections of a signal. And that signal is what's called the stochastic background. It's the for those frequencies of gravitational waves you mentioned, Doug, that's actually the frequency not for emerging neutron stars, but for orbiting supermassive black holes. So much longer wavelength, like you pointed out, on much longer timescales, and it's nanohertz, right? So whereas LIGO, it's like
Hertz, basically.
12 times faster orbital frequency. So the first signal has already tentatively been measured. That is the background of all the supermassive black holes, binary black holes in the universe, basically together. But with the DSA-2000, for the first time, we'll be able to separate out and detect individual binary supermassive black holes. I'm talking about black holes with the mass of 1 billion solar masses that are orbiting each other, right? And they're basically at the center of the mergers of giant galaxies. Every big galaxy has a big black hole in the center of it, and those black holes can merge when those galaxies merge. And that process has happened for our own galaxy and other galaxies, basically. But we can detect that for the first time with the DSA-2000.
Amazing. Yeah, radio astronomy is about to be completely different. I noticed that up at the long wave array, you mowed the grass.
So
that was my suggestion. In fact, by the way, I told Mark that they needed to get rid of the vegetation because it was going to ground out the antennas.
It does. It absolutely does. We actually have to get a weed whacker out there and take the sagebrush down. This is a very sensitive. Go ahead.
Instead, hire. And I'm not kidding, because it's done, a goat herd to bring a bunch of goats out, because they don't create any RF interference like a weed whacker would.
They don't. That's right. The only problem is that our antenna is the perfect height to scratch on.
Oh.
What happens is cattle, or in this case goats, come up and they just scratch off the antenna, and the antenna rotates by about 4 inches, and suddenly our calibration is off.
That's out of phrase.
Yeah. You're exactly correct. It does, in fact, short out the antenna. And even when it's proximate to the antenna, these are cheap dipoles, but it's a very sensitive experiment. It distorts the beam of the antenna, right? It's got mutual coupling effects to the antenna that are problematic for us. So you're 100% spot on. We have to keep those under control.
Yeah. Nice. Very nice Wonderful presentation. Let me ask really quick one question, and we can continue privately. I'm going to have a tour of people coming up to OVRO this summer, and I wonder if we could use your presentation.
That should be possible if I'm in the country, for sure. Yeah, that could be done.
Okay, good. I'll talk to you more about it later.
Yeah.
And are there other questions? Questions from the audience? Well,
I have a question about if you could show do you have a slide that shows the current three-armed array that you're using? You've got three separate regularly spaced arms that are coming off of
The DSA-110, I can show that
Yeah.
for sure. Yeah, bear with me a second. I'll pull up the requisite slide. There we go. Just take me a second to pull up the right one. This is the here we go. This kind of just shows it somewhat crudely, but gives you a sense of this is more detailed.
any of them will do.
Here we go. All right, is that showing as a single slide? So this has way more detail than needs to be seen, but correct. There are 95 antennas on this T structure. Now, actually, only the east-west arm is currently finished. We're still finishing the north-south arm. Then there are 15 antennas that are spaced all the way across the site that were trenched in by optical fiber and power across the site. And yes, there are a dense, evenly spaced array of antennas on the east-west arm, and we're finishing off the north-south one to be the same.
Is there an advantage to that even to being evenly spaced? Is that an interferometer requirement?
So yeah, so there is an advantage. So for how this actually works, the antennas in this T structure are used for detection. The data rates to try to actually search at a millisecond time resolution across a large area is very, very hard. So what we do is we actually search using those 95 antennas, and we keep the signals, we buffer like a time machine, we buffer the voltages for all of these other antennas. And to actually form those beams, you could, how you form those beams, you can actually, in every direction, you got to delay all the signals from every antenna to form a beam. But if they're on this linear spaced, if they're linearly spaced on on concrete like we have here, or on anything, if they're linearly spaced and evenly spaced, you can take advantage of the fast Fourier transform to form those beams. That's the advantage. It's actually bad for when making your images. It's a bad thing to have evenly spaced antennas, but for searching and forming the beams, you can use that fast Fourier transform, which saves us a huge amount of cost computationally.
That was my question, because in computer science, I would want to randomly space them.
And that is the right answer. The DSA-2000, for example, will have them exactly randomly positioned. You want the least amount of structure in their positions on the ground to give you that nice, what I described as a point spread function. There's a Fourier transform between the relationship of their spacings and that point spread function. And the VLA, for example, was built before people realized this, and it's on these Y-shaped structure, which is bad.
Thank you.
You're welcome.
Greg, could I ask a question at this point? Ruby Barn spoke with us back in September, and she's concerned with the 21 centimeter line of hydrogen. She's looking for signals from the epoch of reionization. Is the DSA-2000 an instrument that could be of use, could be of help to her in the research that she's doing?
So she's actually my postdoc, and she will not be using the DSA-2000, but will be using the array she mainly uses is actually the one behind me that I described, the LWA, the dipole array. That's the array that she will be using for that science. And the reason for that is hydrogen produces emission at a very particular frequency, 1.424 gigahertz or 21 centimeter, right? Now, she wants it to be able to target epoch ionization and even an earlier epoch, cosmic dawn. That's so far back in time that even stars haven't formed. So a telescope like JWST can't even probe that far back. We have no probe to that era, right? But we can see the neutral hydrogen of the universe. But that era is so far ago that the 21 centimeter signal that was produced by that hydrogen has redshifted from 1.42 gigahertz down to below, to about, between 50 and 150 megahertz. And that's too low a frequency for a dish like the DSA, but it's perfect for the LWA array that I mentioned. So she is actually using that array, and that would be the most sensitive array for the wavelength, for the cosmic dawn signal, actually, in particular. Does that make sense?
Well, yes, it does. Again, something that I gotta think about for a while. But yes, it does. Thank you. Other
Let me
questions?
ask
Anybody?
sorry.
Go ahead.
Let me ask a question about the pulsar timing with respect to gravitational waves. Are you measuring the total path length difference that affects the timing? Or are you getting other components? And can you characterize gravitational waves?
Yeah, it's a more complex measurement. It effectively is measuring over a very, very long amount of time the variation in the arrival times from an array. Your telescope really, your gravitational wave telescope is really the pulsars that are around you, right? And each pulsar gives you a blip, every few milliseconds in some cases. And over time, you can measure that period more and more precisely. And what happens when you have, as Doug kind of alluded to, when you have the what's actually happening because of these merging supermassive black holes is that space-time is distorting, right? At these by a very, 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 very tiny amount at those nanohertz frequencies. So 1 to a billion seconds is the period, we'll say. And you can use the array of pulsars and measuring their timing very precisely to actually measure that distortion of space-time.
You also get a measurement of the position of the Earth, and I wonder in the laboratory, if we want to sample a radio signal and we can't measure it directly, we can sample a phase of the sine wave it makes, and we can determine the frequency out of that. Can we do that with gravity waves? Like, instead of spending 31 years to measure the gravity wave, can we sample the phase of it and interpolate what the actual wave is?
Yeah, there is some analogy to that. Yeah, with radio telescopes, we can actually sample, intrinsically we have to sample the phase to be able to do interferometry. We have to be able to, and the same applies to gravitational waves for sure. There's ways to reconstruct direction, for example, amplitude. The primary thing we want to measure initially is what's called the Hallinan curve, which is a way of measuring the time of arrivals across all the array and how that might be distorted in a characteristic way, in a quadrupolar fashion by those black holes.
That's going to be spectacular. I almost can't imagine how how different and wonderful that's going to be.
Yeah, it's very analogous to LIGO. LIGO also blows my mind. LIGO can measure the distortion
Yeah.
of the Earth by one atom.
Yes.
Right? It's incredible, right?
Yeah, they're having problems with the coherence of the laser because it's one atom off or something.
Yeah.
LIGO is probably the Cadillac or the Ferrari of technology because things are so finely tuned.
It's incredible, yeah. Quantum effects are incredibly important in the design of LIGO. It's pretty spectacular.
You could bump your desk at Caltech and they'd see it in LIGO.
Absolutely. Yeah, you know, it's isolation from terrestrial effects are a major factor, and why there's a plan to build a space-based one in the future.
Yeah, amazing. Thank you. Oh.
Other questions? Anybody, please step in, step up.
Oh, we should say that if people that are watching want to visit OVRO and really see the equipment and get a tour, that's possible.
That's right.
I've done that before. It's a neat place to visit. When you're looking at pulsar timing for the gravitational waves, you're looking at gravitational waves actually encountering the pulsar. And is there an effect of the distortion of space-time between you and the pulsar, which is a pretty long line of flight, which could confuse things terribly?
Yeah, you're basically sitting inside the array, right? So your times of arrival are coming from different directions, basically, right? And you're right. So you're sitting inside space-time that's distorting, including the pulsars, including the Earth. But we have pretty good sense of the locations of these pulsars. The directions are very precise, and you can reconstruct reasonably well with time both stochastic signal of all those. What's actually distorting the space-time are those those orbiting supermassive black holes. So we're talking about like 10 to the 9 solar mass objects that are orbiting each other, right? At that nanohertz kind of frequency. It's incredible. But you can reconstruct with that network of pulsars the direction, the impact locally, the impact at the pulsar, etc.
So you're looking at the distortions of space-time local to the Earth as a result of pulsar timing, or are you seeing the distortions? How is it distorted over there as opposed to down here?
Yeah, the effect you expect to measure as a function of direction has a very characteristic behavior, and so looking for that shape, a quadrupolar shape of distortion across the time of arrival to the pulsars as a function of direction is the characteristic signal that's been looked for.
Cool.
And the FRBs are also like really cool. There's a question here about research papers about FRBs. FRBs are probably one of the hottest topics in astronomy right now, and Avro's been at the cutting edge of that for quite a while, including the DSA really leading the way in that regard. And if you want access to research, someone's asking about research paper access. Yes, all of the papers that we produce are available for free on what's called the archive, ARXIV, and some of which are linked from our website. We actually, using technology built from the DSA, localized or found the first FRB in our own galaxy in 2020, and it was one of Nature's top 20 science results of the year.
Well, Professor Hallinan, wonderful presentation. Thank you very much. Thank you for spending the time with us today. And you've been very generous with your time, and we appreciate it. But we're getting almost to the point of an hour and a half, and probably we need to wind the meeting down. To do that, I'd like to mention two things that are coming up here at the observatory. First, next weekend, Friday, Saturday, and Sunday of Thanksgiving weekend, the docents Palomar Observatory will get together in the museum where we are now and the visitors gallery to greet our visitors and talk with them about the observatory's history, its telescopes, and the scientific contributions this institution has made over the past 86 years. This is our reopening celebration. The gift shop will be open, and on Saturday, November 26th, docent Ed Rumsey will have a telescope set up near the visitor center, specially equipped for viewing sunspots and solar prominences. Although there will be no tours that weekend, please don't fight the traffic on the roads. Don't fight the crowds in the stores. Instead, drive up to the observatory, and we want to meet everyone in person right up here. Second thing I want to mention, the Greenway Talks online will continue on Saturday, December 3rd at 11 p.m. Pacific Standard Time. Long-serving docent Curtis Coulee will tell the story. Excuse me, Curtis?
Who's
You
that?
said
Who's that?
11 p.m. I assume
I
you
said
meant
11
a.m.
p.m. That's because I was here really late last night talking to a group from Sacramento, and it seems real late to me at the moment. Sorry about that. 11 a.m. Curtis, you're going to do the history, right?
Right?
Looking forward to it. Looking forward to it.
So am I.
Well, that's what's coming up. So again, thank you, Professor Gregg Hallinan, and my thanks as well to all of you over Zoom and people here in the museum, live audience. Thank you guys for coming. Thank you for staying through this. I appreciate it. And with that, I'll close the meeting. And
Thanks,
I hope,
folks.
excuse me?
So thanks, folks.
Thank you.
I hope we'll see everyone next weekend and again on December 3rd. Guys, thank you very much and have a good Thanksgiving holiday.